Otherwise, best if I erase what I did, so I keep them in order, you know. All right, so the theorem that I'm about to write up here basically just collects together the calculational wisdom that we have perhaps just sorted through, and just like a takeaway, just a takeaway. How do you calculate the tangent space and the normal space for a implicitly defined surface? All right, so that's what we're going to write down here in just a second. This is theorem 5.25, that's right. So if we have, sticking with my, I should have not erased this, G from RK cross RP to RP, right? Level function defining, can't spell, defining S equal to G inverse of C for some C in RP, then see that P and the point P are not the same P, are they? Oh well, no one's confused about the dimension P versus the point P, right? Oh well, tell you what, then G subprime of P naught, right? You can write it as the gradient of G1 gradient of GP, right? At P naught, right? And so just getting to the point, we can write the null space at P, listen to me, the normal space at P naught to S as, well, one way we can write it is simply the span, right? The span of, span of P comma gradient G sub, this is not in the notes, but I'm just writing it out, okay? Gradient of G sub I at the point P naught, right? Such that I equals to what? 1, 2, P, right? So the normal space is P-dimensional, and it's formed from the span of the gradient vectors. Now, to be fair, I think I have to put a transpose on these, technically speaking, in my formalism. The reason for that, and I don't think I was being careful up here, I owe you some transposes, because I've made the gradient a column vector, so to be fussy, to make it into rows of the Jacobian, I need transposes. If you look back, I did have that when I discussed how you could parse the Jacobian matrix either as a bunch of column vectors glued together, partial derivatives, or as a stack of gradients transposed. But that's just because I take column vectors as primary in my formalism. So yeah. And then of course, on the flip side of this is exactly like, you could think of this as P naught Cartesian product with the column space of G prime of P naught transpose. See, because the transpose of, and so here G prime, I mean the Jacobian of G at P naught, right? So if you transpose it, you've literally got gradient of G1 at P naught, gradient of GP at P naught, like that, as your columns. And so this is nothing more than the column space of decorated. You know, it's the column space of G prime of P naught transpose decorated with P naught, if you will. This language decorated, I don't think is in my notes. I just thought of it. I think I like it though. And then what's trickier, right, is defining the tangent space. But we can work out that the tangent space at P naught of S, right? It's the normal space at P naught of S, perp by definition. All right, that's actually the definition. But the theorem, if we look at that, right, we're looking at what, like, we're looking at P naught, comma V, such that what? Such that what? V dot what? V dot the gradient. Well, let me be more specific. It's just V dot what? V dot W is equal to 0 for all W in the column space of G prime of P naught transpose, right? But if you look at that, let me just unravel that. So this would literally be like, so remember, if you can define the span, if you can define the orthogonal complement on the basis, theorem from linear algebra, the orthogonal complement of a basis is the orthogonal complement of the span of the basis. So a basis for the column space here is taken to be the gradient vectors. Now that's assumed. When that's loaded into, I really should say, k-level function. And that needs to mean that at the points of the solution that we're interested in, the gradient vectors are actually linearly independent set of k linearly independent vectors. If I have points for G where that's not true, it wouldn't define a k-dimensional submanifold anymore. I don't know what it would do. It would be something else. But anyway, so here, gradient of G1 is like one of them, right? At P naught transpose times V is like one of that's like one of the equations, right? Equal to 0. And then you've got gradient of G2 of P naught transpose times V is another one of the equations. And so forth and so on the story goes. Eventually you get to the pth one of these dudes, right? And if you look at that, you go, wait a minute, I can just look at that collectively as, yeah, exactly, it's just this, right? Which I could just look at as the Jacobian of G at P naught transpose times V equals to 0. Which then means that I can more elegantly state this simply as P naught Cartesian product with the null space of G prime of P naught transpose, I believe. All right, so then I have an example, but I think I did a good example last time, so I'm going to go on here if that's okay with you. All right, so next up, I define a k-dimensional patch. So I'll go a little bit quicker through this because I think this requires less, I think this one's easier. So if we have a R is a actually, can I erase all this?
I'll take a picture.
Go for it. All right. So Sorry, if I hadn't made this stupid mistake in the earlier theorem, we'd have had time for a good example here, but I know you're going to be gone later in the week, and so I'm just trying to get us to a good spot before you have to go. So next up, we talk about, you know, how to define a manifold from the parametric perspective, submanifold of Rn. So I let R, oh, I'm using R for the notation. I guess I'm using R for the mapping. Yes, I am. All right, fine. So that's weird, but whatever. R is a mapping from the domain of R, which is a subset of Rk, all right, to S, which is a subset of Rn, defines a k-dimensional patch of S. All right, k-dimensional patch of S. And the tangent space and the normal space at P are given as follows. Actually, my bad. I think I have. I'm sorry. Let me finish the definition. I'm a dummy. I was skipping ahead to the theorem. My eyes just jumped on the page. So this k-dimensional patch of S, if and only if R prime of I used T there. Wow, that's really. Let's say R prime of X instead. I don't like using T there at all. Man. Whoa. No. I use T for, no. That's not a good notation. I disagree with my notation. If R prime of X has rank K, for all X in domain R. And we also call S a k-dimensional parametrized subspace of Rn. So let's say this, if R of domain of R is equal to S, then we say S is parametrized by R. We can also call it a k-dimensional parametrized subspace of Rn. Of course, you could encounter the situation where one patch wouldn't do it for the whole thing. You might need multiple patches to cover, a more interesting thing. Then, all right, so let's draw a picture. Picture is a little bit easier this time in some sense because we have Rk, right? And then here's my, surface. And again, can look at Rn for lack of imagination as like an Rk down here or in a, Rn minus k up here or something. I don't know, whatever. Just a stupid picture, but if I have, tangent vectors up here, how can I build a tangent vector like that? Well, I can over here. Yeah.
Can you remind me what R prime X has rank K mean?
Oh, sure.
Magnetic has rank K.
Yeah. We can do that. So here, this notation. Keep in mind that this is my other notation for the Jacobian of R, yeah. All right, at the point X. And the rank is the dimension of the column space equals to K.
It has K.
right. Yeah, we have at least k linearly independent column vectors. In other words, there are k linearly independent partial derivatives. Which, in other words, that all of the partial derivatives of R are linearly independent in this context because there are just k of them to take.
Mm-hmm. Yep.
All right, so, let's see here. So, well, let's see if I'm not, have I actually proved the analog of the theorem we did at the start of class today for this context? I guess I haven't. I got burnt out when I wrote this chapter. I must have got burnt out on the existence aspect for the level set, because it seems like I haven't quite done the analogous existential work, if you will, to show that there exists a tangent space at a point to such a thing, right? But let's try it out for a minute, and if I get stuck, then we'll bail. But so let us suppose that here we're at. I think I'm going to use U for the parameters, Scott, if you don't mind. I'm going to use U for the parameters, just for the sort of for the moment. No, I don't want to do that either. Well, I'm going to leave it, but sorry, Ernesto. I'm trying to make a decision here. So let me just I just got to call it something. So let's call this point x naught, okay? Then if this point up here is well, not r, not gamma, but r, big R of x naught, right? Let me call that point p naught, because that's really what we want to describe. We want to describe the tangent space there, right? So if I have a copy of the reals over here, and I take a path that takes time over here and gives me this path over there, like say gamma, right? Then of course I can look at. I'm just run out of letters here. I can look at psi, let's say, of t as equal to r of gamma of t, right? In other words, r goes from here like that. So I can take the path here and I can paste it up there like that by using the patch, and then I can study the relation of the derivatives. Like how's this go? Well, psi prime of t, right, is r prime of gamma of t times gamma prime of t by the chain rule, where of course that's understood to be the Jacobian matrix, and we're talking about column matrix multiplication here. And of course, if I look at psi prime of 0, well, that's r prime of gamma of 0, which I'm going to assume is, by the way, I'm going to assume that gamma of 0 is x naught. So this, when I plug in gamma, that would be x naught, I guess, yeah. Right, and then of course I've got my gamma prime of 0. So I guess we could define, we could define the tangent space at p, p naught to s, right? To be what? We could make it like p comma v such that what? Such that there exists gamma mapping from, I guess in my current language I better use psi, right? There exists psi from r to s and let me use gamma. I'm a dummy. Gamma, such that gamma of 0 is p naught, and gamma prime of 0 is what? P, right? So with regard to, then the question is, and then suppose I define the vector space structure, alleged vector space structure on the tangent space here in the same way I did for the level set. All right. So is that legitimate? Is it the case that, you know, if I have two, you know, suppose there exists, you know, consider PV1 and PV2, right? Elements of the tangent space at P of S. I'm going to drop my subknots if that's all right with you. Then, right, there exists what? There exists gamma 1 and gamma 2 from the reals to the parametrized surface we're considering, such that what? Equals to what? P. And also we have gamma 1 prime of 0 is V1, and gamma prime 2 of 0 is is V2, right? Wonderful. So then, how do you construct, I want to construct at the moment, I know this is a proof in search of a theorem, isn't it? So I want to, my goal, construct gamma from the reals to S, right? For which, of course, gamma of 0 is P, but also gamma prime of 0 is, let's say, V1 plus V2. And we believe if we can do this, we'll be able to do scalar multiplication just the same, right? It's not going to be a problem. How do you do it?
Gamma has to be B.
How about this? R of R inverse of P plus T times V1 plus V2 maybe? So like this right here, right, is nothing more than like, it's like, you know, that path would be like R inverse of P, which I'm calling X naught for the sake of, well, let me just, this point P, this would be R inverse of P, okay? Finally, my X naught. If you want to, I can add knots on these P's. I'm back to that again to make my picture coherent. Fine. Right, so this is quote unquote X naught in my picture, right? And then this is k-dimensional space, so you can just take your v1 and v2 vector. Oh, can we do that? Can we take the v1 and v2 vectors? No, we cannot, because v1 and v2 are what? Where are they? They're in Rn. Like v1, v2, they're like up here. They're n-dimensional vectors, so I can't quite do that. But I actually think I can reasonably do the following. Check this out. Just or maybe more to the point, more to the point perhaps, just do this. P naught plus T times V1 plus V2. There you go. How about that? How about me not be an idiot and point out that it's really, really simple to see how to build the curve? Because, listen, if I want a path up here that has V1 plus V2, I just take the line in n dimensions, which has base point P naught and has direction vector V1 plus V2. I can do that. It's allowed. We're in Euclidean space. You can write down the equation of a line, and manifestly, d gamma dt is what? V1 plus V2, right? And so, yeah, if you plug in 0, still V1 plus V2. And so, yeah, no matter what pair of tangent vectors you pick to the parametrized tangent space at a point, I can, of course, construct a line through the point which has the sum of the vectors, right? And so, yeah, we can define addition of tangent vectors at the point meaningfully with the assumption, in fact, that yes, there does exist a curve which takes it as a tangent vector. So that's probably why it's not in the notes. It's just too obvious to me when I wrote the notes, but it's become unobvious to me since I've been away from it for a bit. We good? So the theorem then is, well, okay, great. So how do you calculate these things? So the theorem, go for it. And I guess I probably should stay over here, actually. So with this setup, the tangent space to P at S is equal to the column space. Excuse me, I have to decorate it. P, Cartesian product with the column space of R prime of P. There you go. And the normal space to P at S, well, it's the tangent space to P at S perp, which is literally the decorated null space of the transpose of R prime at P, if I remember correctly. And the calculations are actually very, very similar to the ones we already did. So that's the theorem. I won't belabor it much more. But I will try to do an example, finally. Ooh. That's not good. All right. So let me just make one up. There's some examples in the notes, great, but it's healthy for us to make up a new example. So R, and let's say of x, y, z. In fact, maybe I shouldn't use x, y, z. Let me use u, v, w. Just that's kind of more akin to the calculus 3 notation, and wouldn't be bad for us to use some different notation. R of u, v, w is equal to, let us say, u, v, v, w u squared plus v squared and v squared plus w squared. All right. 1. Now, by the way, before I came to my senses and just wrote the line proof for the last thing, you might have asked the question, how did I know R inverse exists? I knew R inverse exists locally because of the inverse function theorem. See, because we're assuming it's full rank, meaning that the partial derivatives exist at the point, yeah, so. Anyway, so here we go. Here's your this would ostensibly be 1, 2, 3, 4, 5. So we're looking at a allegedly, this is an element of S, which is a subset of R5, right? So, but we're looking at a three-dimensional a three-dimensional manifold in R5. Okay, and just for some language, let us give the coordinates in R5 of x, y, z, oh man, v, I'm trying not to use u, v, or w, a, b, all right, there we go, that's weird. Maybe not a, b, I don't like that. Golly, x4, x5, there, I made it ugly. Okay, there you go. We'll use those as our Cartesian coordinates there. Okay, in other words, if you wanted to think of it in terms of parametric equations, you have x is equal to uv, right? Y is vw, z is u squared plus v squared, x4 is v squared plus w squared, and x5 apparently is equal to 1. So there will come a point later in the course where we want to think like that. So I'm just writing that down as kind of something to keep in mind. All right, so what's the Jacobian here? What's R prime? Well, we've got ourselves a oh. Okay, so R prime would be partial R, partial U, partial R, partial V, partial R, partial W, right? Because R is a mapping from R3 to R5, which makes it a 5 by 3, 3 columns, each column 5-dimensional. Okay, so easy enough. Partial U, I get myself a V, a 0, a 2U, a 0, and a 0, right? And then what's partial v? Well, partial v, I get a u, a w, a 2v, a 2v, and a 0. And then partial r, partial w, I get myself a 0, a v, a 0, and a 2w, and a 0. So there's the Jacobian of this thing. And in order for us to be, all right, so like I should choose, technically speaking, like, so we'd like to define the domain of R to only include UVW for which, you know, the dimension of the column space of, you know, R prime of UVW is equal to 3. So that's a question that's maybe one you haven't thought about before. How do you judge whether or not this 5 by 3 matrix has rank 3 if you've got variables?
I need to see if those 3 columns are linearly independent.
Yeah, how would you test for that?
I can set it equal to 0.
Mm-hmm. Well, sure, but how would you test for it in terms of, like, is there some criteria you could tell me? I mean, yeah, of course we could take linear combination, set it equal to 0, and then work on that directly like that, sure, but is there like a simple calculational thing we could do without introducing C1, C2, C3 for the linear combination, right? Just in terms of the functions which are in front of us. Well, I'll tell you. So one of the things we could do, I mean, and there are many choices, all right? But one criteria which would suffice is if we could look at this 3 by 3 submatrix, and if you had the determinant of that, see if that determinant was non-zero, that would imply that those subvectors of the 5-dimensional vectors are not linearly dependent, which then implies that their extensions are also linearly independent. See, like, now if you get that this is 0, there's still hope. It could be that the remaining components distinguish deny the linear dependence. So the only way to be sure you have linear dependence, I guess, would be for the vanishing of all possible subdeterminates.
So if that 3 by
3 by 3
is invertible,
yeah,
then I get linear independence.
right. Now, but this, of course, we can calculate too, right? Because we got like what, v times minus 2v squared, right? Minus u times minus 2v squared and 0. So that gives me like a what? You got yourself like a v squared times what? Minus, let me pull the 2 out. I got like a minus 2v squared times what? Times like v plus u. So if I want to be lazy and just kind of be like, all right, well, now if I had instead chose the lowest 3 to make my subdeterminant down here, it wouldn't have been as helpful because I would have automatically got a 0. But that wouldn't have said that it's impossible. It would have said that determinant's not helpful to me. Listen, there's an easy question to answer here, and there's a much harder question to answer here. Easy question is to define, to find a set which could serve as the domain of R. The harder question is to find the maximal set which would serve as the domain of R subject R conditions, right? So hey, this is enough. We can just go, okay, we're going to let domain of R be, for us, we're going to just let it be UVW, right? Such that what? You know.
Base not equal to minus.
Right, so yeah, V such that V is greater than 0 and U is not equal to minus V, yeah. So to be more specific, we could make our life easier and we could say, okay, so we're going to just let it be, we're just going to use 0 to infinity, right, squared Cartesian product with the reals. We could take that as our parameter space just to be lazy. That would be interesting enough. There's no need to, W can be whatever, it doesn't, there's no, isn't that funny? It doesn't seem like W appears asymmetrically from V in these formulas to me. I have a suspicion that if we looked at a different subdeterminant, we could just as well have concluded like we could let like U be free, provided that V and W satisfied both being positive or something like that. I don't know. So again, we're not trying to find the answer to all possible choices of domain. I would just point out that settling the domain question can be delicate. Okay, now that we have it, we can pick a point in the domain, and we can find the tangent space. Listen, so the tangent space at an arbitrary point in the domain is what? TP in my chosen domain, all right? TPS would be like, you know, the span of like, you know, P, comma, partial R, partial U, P, comma, partial R, partial V, P, comma, partial R, partial W, right? Such that, you know, the derivative is evaluated at P, okay? So I can describe the tangent space for you at an arbitrary point on my surface without, you know, sweating. And I could have done the same at an arbitrary point to the normal space in the previous example, because it's just the gradient vectors and you plug in the point of tangency and that's it. However, I don't like my chances so much at calculating the perp of these for arbitrary functions. Maybe you could, I don't know. But usually if I'm asking the question about, you know, the other side of things, then I want to, okay, so here's a game, there's two different games we can play here, Ernesto. One game we can play is simply to pick a point, right, that's in my space. Like, for example, we could set P equal to, oh, I don't know. I mean, in the domain, this isn't P technically. We set P equal to R of 1, 2, 3. There we go. That's weird enough. 1, 2, 3. And if I plug 1, 2, 3 into here, I get that P comma V is in TPS. I get V, V1. I can get, you know, what does that give me? 1, 2, 3. So 2, 0, 2, 0, 0. There's my partial R, partial U. partial r, partial v evaluates to what? Partial r, partial w evaluates to what? Partial r, partial v. I got plugging in 1, 2, 3 into that. I get 1, 3, 2 times 2, 4, 4, 0, and my w, I get myself a 0, a 2, a 0, a 6, a 0. So there's my, those form a basis once decorated for the tangent space. I'm really liking this decoration for the tangent space. And of course, we could just shove those in a matrix and calculate the null space of it, and the basis for that would then be the once decorated, the basis for the normal space. We could guess, like you can tell me easily. Well, first of all, so that would be the span of those guys decorated would be the tangent space at that point. What would the I can tell you this much. The normal space, good grief. I say normal space, I write a T, dummy. So the normal space at 1, 2, 3, not 1, 2, 3, but this. If I plug 1, 2, 3 into this, I get, actually we're talking about the point 2, 6, 5, 2 squared plus 3 squared is 13, and then 1, right? This right here is R of 1, 2, 3, okay? So the normal space of that, I can tell you, it is, 2, 6, 5, 1, 13, 1, Cartesian product with, like, the span of what? Well, I can easily tell you one of those vectors. Can you tell me? Tell me a 5-dimensional vector which is perpendicular to all 3 of these dudes. Oh yeah, 0. Yes, 0 is always a choice, but not the interesting one. That's good though that you're thinking that. Like that's honestly, it's very good, but we want a basis, so 0 is out of the running. I want dot product to be 0 with all 3 of these vectors.
Yeah.
There's one I can see without calculation.
Okay. Everything's 0, but the third vector. No, sorry.
Yes, everything's 0, but the last component.
Okay.
Yeah. Because if I just make it 0, 0, 0, 0, 1.
Yeah.
So from the perspective of differentials, this is not surprising, see, because up here, dx5 is 0. So like, that has something to do with this. Anyway, that's a mysterious future comment, but, so, okay, there's one, so the uninteresting way to finish this calculation is to make this into a matrix and then do row reduction to find the basis for the null space to find out the other vector. But I want us to try a really different way. I want us to ask a really interesting question, a slightly interesting question, which is, how can you recast this 3-dimensional surface as a level equation? See, because if you can do that, then you can just take the gradient to the level functions, and that's easy. There's no need for the, I mean, okay, admittedly, this isn't that hard either, but if we can do this calculation, if we can find the level function for which this is a parametrization, well then, we can calculate the normal space at a point just like we did this one. We can find it at many points at once because we don't have to go through that calculation. So can you tell me, what are we up against? Well, let's talk about what we're up against. We're up against a system of nonlinear equations is what we're up against. We want to eliminate u, v, and w in favor of x, y, z, x4, and x5. If we can do that, then we can recast this as a solution set to a system of equations. So how do we eliminate those things? Now, how many independent equations do we need? We just need 2, because it's a 3-dimensional subset of a 5-dimensional space, so 2 independent equations will do. We just need to find 2. Okay, so 1 independent equation will do. See, because we already have this one. That's gold. That means, what that means, honestly, Ernesto, is this is not a genuinely 5-dimensional problem. This is a 4-dimensional problem masquerading as a 5-dimensional problem. That's the truth. That's the man behind the curtain here. What games can I play here, maybe?
X over Y.
Oh, X over Y, I like that. That's a nice game to play. That's a very nice game.
U over W.
So that gives you what? The V's cancel? U over W, okay. So, oh, what about Z minus X4? So subtract these equations, right? Then we get U squared minus W squared, right? So close. So we could solve this and get W is equal to like U times X over Y, right? And then we can plug that in down here and we'll get Z minus X4 is equal to U squared times 1 minus X squared over Y squared, right? Factoring that U squared out. Well, nope. Rats. Yes. Drat. Thought I saw it. How do I get rid of that U? Let's see here, xy is uw v squared, and that is equal to uw, z squared is, v squared rather, is z minus u squared. Well, that didn't help. My last step was not productive. I mean, I'm not sure we're going to be able to solve these. It's, you know, it doesn't have to work out. You know, the existence of an implicit solution and the manifest algebraic production of said solution from, you know, finite number of algebraic steps is two really different things. But these are relatively simple formulas, so I have hope still that we're going to be able to get it. Listen, if I somehow isolate the u, right? I have two equations with u, right? I have two equations with u. I've used both of them here. Well, no, I used the top one to get this x over y equation, right? But I haven't used this one yet. And so that tells me u equals to what? Well, it tells me u squared is z minus v squared, right? Now the annoying thing about that is it brings in a v squared, which I don't want. And I can trade that v squared for z minus x4 minus w squared, right? But now I've got this annoying w squared, right? But I do know that I can solve u squared is equal to z minus, I'm probably going to, see, this is the kind of thing, if you're just kind of like doing it and not paying attention to where you started and where you've been, you'll find yourself getting like 0 equals to 0 eventually, stuff like that. And I may be on my way, I may be on my path to that. But well, I got rid of the u squared, but now I've brought in w squared into the fold, which is annoying. You know? Maybe if I look at squaring x and y, like x squared plus y squared is v squared times what? V squared times u squared plus w squared. And u squared plus w, well, if I add these two, right? Z plus w4, z plus x4, it's equal to 2v squared times plus u squared plus v squared, right? Plus u squared plus w squared. So I can trade u squared plus w squared for a v squared times zx4, z plus x4 minus 2v squared. That's kind of nice. See that? That is at least just a v in it. Does that? Was my other, I had I guess maybe yeah, I don't know. At this point, it's definitely easier just to go back and find the find the null space to this thing for the point in consideration. But anyway, these are the games you get. It's not an immediately obvious question. It's not an immediately obvious thing. What is the level equation for which a given parameterization maybe is the parameterization of? Like sometimes they're obvious, but this one not so much. At least to me at the moment. Let's see here. I think that's pretty much it for what I have